Kris Hunter is a battery industry consultant, and she's consulting under the name of THCEX Consulting out of Grand Rapids, correct? Oh, out of Holland. Thank you. She is dedicated to advancing a circular battery economy. She previously served as a director of the business development at ATC Drivetrain, a global battery service provider. Hunter has a bachelor's degree from Grand Valley State University and an MBA from DePaul University. You've probably read, if you're interested in EV vehicles and modern battery technology at all, you've probably read that all these huge batteries that are in our cars now are someday going to end up in a landfill. That's a myth, and Kris is going to address that question today in a great amount of detail. So, without further ado.
Thank you. Thank you. Topic I love to talk about here. And I will say, I used to teach adjunct at Davenport in Grand Valley, and one person in the front row, couple in the second row, the cool kids sit in the back. So it holds true throughout your life, and the ones online are even cooler, right? So this is, this is great. There you go. Well, it's a pleasure to be here, and I'm really excited to talk about this. I'm glad that there are other people that are interested in this topic. It's sort of unusual and not a typical part of the industry, but I think a very important one, and it becoming more and more important as we start to see some of the older batteries now coming offline, and some of the new technologies around batteries that are going to help support what we're doing in this space. But before we dig into that, I'm sort of curious about, I see a few people from the EV special interest group from HASP here. So I know we've got a few EV owners. Raise your hand if you drive an EV. Yeah. Yeah, exactly. That's interesting. So do you know what kind of EV you drive? Not just the brand, but do you know about the battery in your EV? So who here drives just a regular hybrid automobile, like a Prius or a Civic? Okay, so what about a plug-in hybrid? No. Okay, and what you two? Okay, and okay, which is that. And then the rest, everyone else is driving maybe a Tesla or a large form factor full BEV. So I like to start with this just kind of to give an idea of the differences between the batteries that exist today, and they're significant. So if you're driving a hybrid electric vehicle, the batteries are generally smaller. These are not plug-in. They're regenerative braking generally to charge them. They can also get charged by the electric motor. But basically you've got an internal combustion engine and you've got kind of an auxiliary battery. And those things run and work together to help support, a better mileage for that vehicle. And those batteries have a tendency to slower charge and discharge cycles. They're not plugged in, so you don't have to worry about stopping to fill the battery, which that range anxiety that everybody always talks about. The next step, the next size up, is a plug-in hybrid, and it operates very much like a regular hybrid, still has an internal combustion engine as well as the battery. The batteries are generally a little larger, not always, but a little bit larger that you could plug them in. So for example, I drive a plug-in hybrid vehicle. So I plug my car in at night. I get up to 50 miles on my electric, which works for me most days. I'm just in Holland and driving around. So vast majority of the time, I use my electric motor to operate my vehicle. But I do have an internal combustion engine and a fuel tank, so I don't have to worry about range anxiety. I can continue to drive in a hybrid mode, and that operates that way. And the third, the largest form factor battery, larger size battery would be a full battery electric vehicle or all electric vehicle. And so, significantly different batteries And we're going to get into a little bit about the chemistry differences between those types of batteries, but that's one kind of difference between all of these EVs. There's not one size fits all because there's different types of EVs out there. So I also like to sort of put this in perspective of our area. So in Holland, we know that there is a lot of battery stuff going on. So what have you heard or seen? What are we familiar with here in Holland? Companies that are involved in battery. LG, big one, huge organization. $1.7 billion addition to their facility, 1 million square feet of battery production, huge player. Any others?
Purposes battery packs. Has a business on the north side where they take in battery packs, analyze the cells, break them down, and then repackage them and sell them as a used battery. It's got a pretty good business going that way.
That's great. That's great. So a few others here that I just wanted to point out, you may or may not be familiar with. Obviously LG, huge one. Clarios has a very large facility, old Meadowbrook facility from Prince, and they're producing a lot of lithium ion batteries there. Many of them get shipped to Germany and they're used for various automotive applications. Not very many stay in the US, and most people don't know that Clarios has such a big production here. I got to update my slide. Natron actually announced last month that they're going to be stopping operations. So that was a sodium battery plant. They were doing a lot of R&D, and I'm not quite sure what happened in that space, but we know that tariffs and things have wreaked havoc on a lot of smaller and startup companies. So, I'm not sure about exactly what's going on with Natron, but they'll no longer be operating out of that facility, but Clarios still a big player. We also have Volta. Is anybody familiar with Volta? So Volta is up on the north side of town, and they produce batteries primarily for the recreational vehicle industry, and they're a huge player. So they were just purchased recently by a venture capital company out of Grand Rapids. There were actually kind of a few that went in on this, but that's been sold. It's going to be changed to, I think, Voltagen LLC, but they're producing a lot of batteries and they're shipping all over the world. And we have a lot of other suppliers. Cam Plastics makes some parts for Tesla. We've got ITW Drawform. They're making some Tesla parts as well as some for GM. We've got, lots of other businesses that are in the materials and supply space. And then ATC, my former company, well, I'm still a shareholder of ATC, but kind of a unique service company. Anybody familiar with ATC? Well, we're going to talk a little bit about what they're doing there, and I think you'll be kind of surprised by some of the work that's being done here in our town. Yeah.
Just had a question. When you say make batteries, what do you mean by that?
Yeah, so we're going to talk a little bit about the construction. So that's a good place to kind of step next. So bear with me a moment. So life cycle, we're going to get into this a little bit, and I'm going to talk a lot more about kind of how these things fit together from the formation of a cell, which you can consider making a battery, to the integration of those cells into what we consider a battery pack, kind of the colloquial term battery. We think of a completed unit, but there are some variations in play in how different parts are used throughout the life cycle. But we're going to talk a little bit about, what that looks like and how do we achieve sustainability in this space. And in particular, we're going to focus on this sort of reverse supply chain for batteries. We're going to talk about from the end consumer, when there is an issue, how does that battery get handled from that point all the way back to recycle. So we'll talk a little bit about these battery assets and what they are, make sure we're level set, everybody's understanding kind of what we're talking about here, the different types and form factors, chemistries, etc. We'll talk about circularity, and then we'll talk a little bit about some interesting upcoming and advanced technologies to help support sustainability in this reverse supply chain in this space. Okay. And then of course we'll have time for Q&A, but as we discussed, if you've got a question or if I say something or give a weird acronym, stop me if you need clarity, and I could certainly talk it through with you. So battery assets, there's a lot of complexity in the battery space. And that starts at the very root of how a battery is designed and produced and deployed. We have lots of things that go into the decision process on which chemistry, which form factor, which design of a battery an automotive manufacturer, for example, is going to use. So you'll quite often see, if you've done research on batteries or you wanted to look at your own battery type that you might own, you know, what does that particular chemistry mean? Well, they use different diagrams like the one shown here in the lower part of the picture to make certain decisions about the chemistry that they're going to choose. So there are always drawbacks, you know, benefits and drawbacks to every decision that's made about a chemistry. You can see that, for example, LFP, which is lithium iron phosphate, it's a very common battery chemistry used in a lot of automotive applications. There's a lot of talk about expanding lithium iron phosphate use in vehicles because it doesn't require some of the more costly or conflict materials. But if you choose LFP as a chemistry, a design team would look at this and say, well, okay, so relatively long lifespan, you can see sort of the red line here. We're going to get a longer lifespan, but specific energy is lower. Specific energy refers to the amount of power per weight. So you're going to have a heavier battery. Well, in the automotive space, everything is give and take. So if you're going to have a heavier battery, that means you may need to reduce weight in other ways. So a lot of these different chemistries, all the different mixes within each chemistry, because the percentage of each of these chemicals that's used, kind of the special sauce, usually is not known to everyone, kind of secret to the production. But these obviously lead to a lot of different chemistries of batteries floating around in space, and they don't all act the same. So that means we have to be very cognizant of what we're dealing with, which chemistry we're using, which chemistry we're trying to work on, if we're going to repair or try to redeploy these. So chemistry is an important consideration. Yeah. Yes, they do.
Does LG make batteries with different chemistry?
Yes, they do. So even the same manufacturer will have different mixes, and it might be a different chemistry, different weighted percentages of chemicals in the same chemistry for a different customer. So everyone is unique. That would be the takeaway. Similarly, when we talk about form factors, there are lots of different form factors of batteries. And so by that, I'm referring to cylindrical cells, which look an awful lot like our primary batteries that we use, like alkaline cells, a D-size battery. There are lithium ion batteries that are cylindrical. And so they look an awful lot like a regular battery, but they're very different. Significantly different chemistry, they operate differently. There are prismatic cells, which are generally a hard-sided cell, so they're rigid. And there are also polymer pouch cells, like in your phone, or sometimes we'll see the pouch cells consolidated together to make a module. They have tabs, the plus and minus tabs that come out the top, and they're welded together and put in some kind of enclosure. So form factors can vary significantly as well. There's also variability in cell quality. These cells are graded and sorted by manufacturers. Even amongst the same lot, there can be variability in the cells that come out of one lot. So that means a significant amount of testing goes into these cells, as manufacturers will generally have A cells, B cells, maybe C cells, depending on how they're going to be used, where they're going to go. And the warranty can vary by years. A cells getting maybe a 5 to 7 year warranty, where a B cell might get 2 to 3. So quality can vary a lot. And so that's an important consideration as well. Capacity, we just were talking a little bit about capacity, and that makes a big difference. Over time, capacity diminishes, and so we have to understand and be able to test for how cells are going to operate given their existing capacity. And that can vary based on the production, but also the use characteristics. And then finally, the control systems that go into this. They're always different. The programming, the design, the way that the battery management system has to handle those cells will depend on the chemistry, on the form factor, on the size of the battery itself. And, those are critical parts of our battery system. Any questions on that? So lots of variability in the cells, a lot of complexity in the fundamental basics of a battery. So then there are also different sizes of these different types. So, small polymer batteries that you might have in your phone are very different than the polymer batteries that would be used, for example, in an electric vehicle. They may be very similar, but they're not going to operate quite the same way. When these cells are made, they're grouped together in cell groupings. Cell groupings are put into series or into parallel, depending on what the outcome, what the energy needed is. Remember, series, similar to like the old light bulbs for your Christmas tree. If you take one out, the whole thing stops working. So you might hear somebody talking about the way that a battery is configured and say it's 12S5P. That would be just the classification. So they've taken these cells, they've put them into groups, and they've got 12 of these groups in series to get a certain amount of voltage, and then a certain amount in parallel to give you the specific power. So these are put together in different ways. My point is that you are layering complexity on an already complex product. You can see the difference between a couple of modules here in the center, where we've got cylindrical cells that are potted in some way. There are different materials that are used to kind of hold these cells in place, reduce vibration, maybe provide some thermal management within the module. You can see kind of cell groupings here. This might be 3 groups that are in parallel there, and these are in series. They can configure it in any way to get a certain energy outcome. Here's an alternative, a prismatic cell configuration inside of a module. So these cells are modularized. So we get a kind of a mini pack, and those mini packs then are put into a larger pack, again, put in parallel or in series to create whatever energy we need. And you can see the bottom rendering here is of what a large automotive pack might look like. And it's got different trays made out of different composite materials or metal. And then there's all the bus bars and the wiring and thermistors, and all of these things kind of come together to create this large pack. And what we have to remember is that every one of these components has very specific testing and certification and validation requirements. There are automotive requirements for on-road. We always hear about how there are certain requirements for testing of any equipment that goes into a vehicle. But then there are also special testing requirements for maybe determining if a module is operating in an errant way. It's not working correctly. There might be special testing protocols that are put into place, but testing becomes a very important part of how all of this fits together and works correctly. So, kind of in summary, there's very little standardization here. This is quite a costly part of a vehicle, can represent sometimes half the cost of the vehicle itself in the battery system. And of course, can be very expensive to repair as well, and sometimes not repairable at all. And I included some pictures here because I wanted to show what a typical battery might look like once it's sealed up or going to be sealed up for use in a vehicle. So we've got in the upper left here, a picture of a Tesla pack using 2660 cylindrical lithium ion cells, hundreds that, tens of hundreds of cells that are used in one of their packs, tab welded. And then they also use an epoxy and a foam for thermal management and vibration management. So, very difficult if you were going to try and do any kind of repair to any of the cells there, virtually impossible. And contrast that with, this is a Nissan Leaf pack, and you can see that the focus there has really been on making the modules accessible so that it's a very repairable pack. You can open this pack up. If you have one module that's operating incorrectly, or maybe just a couple of cells within that module, you can still take that module out and replace it. So very different serviceability aspects to all of these batteries that are deployed as well. Some more serviceable than others, for sure. And there's a little more complexity here that we have to at least keep in mind when we're talking about life cycle management. The transportation, packaging, and storage of these assets is all very complex as well. There are differences between fully functioning, like could be a new or just a normal pack that's getting moved around, and how much you might pay to ship that battery pack across the country, for example. But if that pack has had any kind of errant behavior, a small thermal event, for example, maybe even if it's extinguished, that can be classified as damaged or defective, DDR. Then it requires hazmat for shipping and permitting. The costs can become astronomical. So what we have seen, unfortunately, is we see stranded packs all over because it's just too cost prohibitive to try and move them. So that's another complexity. Packaging can be a wood crate, some kind of a plastic crate. I've seen steel crates, other materials, different thermal management materials that they use for packing those. It's very, very complex space. And there's a lot of interesting work being done in thermal management for packaging materials, especially for damaged or defective packs, but a consideration for sure on the service side. And then finally, storage. There have been a lot of conversations and standards being developed around storage. Things like, I was on a conference call with California EPA, this was a couple of years ago, and they were talking about requiring 15 feet between each pack to ensure that they couldn't therm and start like a fire and cause another pack to start on fire. Well, if you're a remanufacturer, even a manufacturer, and you've got thousands of packs, 15 feet apart becomes pretty untenable. So there are just a lot of conversations in this space on how do we approach this and make it, of course, it's important to be safe, but we have to be realistic too about how we're going to manage this. So lots of considerations, and I'm obviously teeing you up to talk about how difficult this space is, but definitely worthwhile. So let's talk a little bit about circularity, because this is the idea of sustainability in the space. We've got a lot of batteries already out in use. It's not slowing down. Battery production continues to increase, and not just for automotive. I'm focusing on that mostly today, but there are lots of other uses, right? We have batteries around us all the time. Your phone, any of your appliances at home, everybody's got an Ego now for your lawnmower. And I mean, we are battery rich at this point, but everything is electrifying, right? So we really think about, how do we do this and how do we manage these things as they start to age out, or if they're damaged and need to be taken care of and repaired. So here's this image I showed you a little bit earlier. And this was something that Global Battery Solutions, my former company, was involved with Resell over at Argonne National Labs in Chicago and Department of Energy and National Renewable Energy Lab on how do we do this and what does this all look like? The idea to redefine, what is end of life for these big, expensive things that we have. And just because it's not operating in your vehicle any longer, is that end of life? Or is there some other way we can use the energy potential in those? So really redefining, and we spent a lot of time thinking about what does end of life for that asset really look like. Realistically, trying to avoid models that require that these assets go direct to recycle or landfill. I mean, keep landfill straight out, right? We got to find ways to handle these without filling up our landfill. So avoiding a direct to recycle model. So that means design for serviceability, design similar to those two packs I showed you that contrasted potting techniques that use something that you can't repair versus a more repairable type pack. So there's a lot of conversations now about design for serviceability to avoid having to go direct to recycle with these things, suitable chemistries for longevity so that they would have not just considering all of those chemistry and form factor characteristics in the design of the car, but thinking in terms of what's going to happen after car. So energy storage, how do we design so that we're able to address both of those lives because they're both very realistic and, giving pathways then to be able to use those assets longer. Export is sort of an interesting one, especially I would say in the last 5 years. There have been more and more conversations about the strategic imperative to keep battery assets here in the United States. Just like Europe says, we have a strategic imperative to keep these assets here rather than shipping them to North Africa. We want those because there are a lot of materials in those batteries that we can urban mine rather than having to buy these raw materials or try to mine them. We're not adding a whole lot of mining capacity here in the United States. So how do we keep up with demand? One way to do that is trying to extract those materials from existing assets that are already out there. So export has been growing as an important reason for design for serviceability and keeping these things out of export routes. Obviously, the most important things are safety first and then efficiency. And so when we think about circularity, those two are the most important characteristics for us. Excuse me. I mentioned urban mining, that's becoming more and more of a topic. And, conflict mining, there are lots of great articles, and I'm sure if you've encountered some of the stories about how some mining operations are used to fund conflicts in different countries. They use a lot of child labor. Those things, how do we manage to not use or have to get conflict materials? If we can use what we already have, that's one way to avoid it. So again, the whole idea is sustainability, and that's really about finding this balance between, the government standards, the human impact, the environmental impact, and the economics of this, to create sustainability around what we're doing with batteries. And, if you think on it, we really probably should have started talking about a lot of those things before, but we're where we're at, right? So we have to think about how do we do this now? So as I mentioned, Global Battery Solutions was involved in a lot of conversations. We got to work with a lot of really interesting organizations talking about how do we manage around this and what do we do in this space to make this this whole thing more sustainable. And one of the exciting things here in Holland, we were all local, kind of, roll up our sleeves, let's figure out how we can do this. Myself and my 7 partners started working on some projects. Our first was a hybrid electric bus project for an international bus manufacturer. We were doing some repair on their packs We developed some in-market repair for them to be able to use their service organizations. So similar to if you went to a dealership to have a dealership work on it, right? And we started to see that there were, a significant number of things that we could do in market to repair those batteries and redeploy them back out. Great. Step number one, minimal amount of disassembly of the battery asset. Maybe it's just replacing a module. Maybe it's just some other component. Maybe it's the electronics or the control systems that I mentioned. So that was step one, repair. Little or no disassembly, do this work in market, get those assets back in their original application, get them back on the road. Great. If there is more work that needs to be done, something a little bit more intense, maybe it is a module replacement, or maybe, it's something where we have to actually open the pack up, disassemble. We employ a remanufacturing concept, which means basically rebuilding this pack. And the idea is to have certain, maybe mandatory replacement parts, certain things that we would automatically just replace. Maybe it's a new electronic piece. Maybe we would automatically replace the contactors, whatever it is that might show some wear. Rebuild that pack around the matching of those cells, get them as close as we can in capacity so that they will operate optimally, and then redeploy that asset in its original application again. So remanufactured assets are a great economical way to repair those parts, get them back into their original application, and keep running that vehicle until battery capacity wears to a point where it's no longer applicable. Generally, when we talk about remanufacture, because we do have mandatory replacement parts generally, and we will replace modules or groups of cells with cells that are either new or at or better capacity, you might get a little bit better capacity in that end product, but it's generally about the same. The next step then, when that battery has been run past its usability in that first application. So for example, many electric vehicles will have around maybe 70% capacity. Once your battery hits 70% capacity, your vehicle says, no, you can't, we're not going to operate. The capacity has to be 71 and higher. Well, 70% is still a lot of capacity, right? That's a significant amount of capacity, not for operating that vehicle, but that energy potential still exists. So how do we take that asset and put it into an alternative application like energy storage, grid backup for utility grids, renewable energy storage systems, some of these large battery packs that they're deploying for wind farms, solar farms. I think recently I read that solar energy has exceeded the pump storage that we used to use as the most widely adopted renewable energy or something capacity wide in our grid. Well, we all know solar is a daylight thing generally. I mean, you get a little power reflection, but the idea is we need to somehow store that energy if we want to keep consistency or a baseline of our power. So great application for xEV batteries. Batteries coming out of cars that still have a lot of energy potential is to employ them in some kind of energy storage system. And we did that here. We built a backup battery system, 11 kW, about the size you'd use for a home, as a demonstration project. We used, these were cylindrical 650 cylindrical cells in a configuration for this hybrid pack that we were working on. We were able to make some adjustments to that. We had to design our own balance of systems products to work with this pack because it's a different capacity level. There isn't anything on the market made specifically for second life battery. Well, there are a few things that are getting launched now, but at the time in the early 2010s, there was nothing on the market. So we had to design all of our own balance of systems products. But building an alternative use for these batteries, and I can tell you the one that we built 10 years ago is still operating over on the other side of town and it's very little degrade because of the slow charge and discharge cycles. So a very good demonstration of that particular technology. Any questions on that? Okay. So repurposing, second life, 2L, there are all these things that they're calling this, but a very, very important way then to keep these assets in use and try to use up the energy potential that's left there. Then finally, when there's no economically viable use for these assets, they're at such a depleted level, or they're just, completely depleted. We want to find a way to recycle them responsibly, avoid the landfill, use, usually mechanical shredding of some kind to extract the black mass, and that material is then refined to get new material to use in production of new cells. So we were able to publish some of our findings here in the Mineta National Transit Research Consortium report back in early 2014 that was published. And then recently we did a second publication back in 2023 with the National Renewable Energy Lab and a bunch of automotive manufacturers. And that was primarily focused on how do we deploy these things in second life. So these things are happening. Very, very reasonable approach, I think, on a complex product. So I want to talk a little bit about some of the advanced technologies here to support this flow, to support this redeployment in second life and this recycling. There are a lot of conversations and standards being developed globally around tracing batteries, not only for, as I mentioned, some of the performance characteristics, but this strategic imperative to keep these assets locally. People don't want these assets to leave their markets, whether it's a country or a block, because these materials are so critical to what we're trying to do in deployment of electrification in general. There's a lot of need to sort of keep track of these. And there are also the social impacts of conflict mining and, being able to prove that your materials are coming from reasonable suppliers and you have, traceability of that asset. In Europe, they talk a lot more about extended producer responsibility. We don't generally like that concept as much here in the US. So we talk about, giving guidance or standards, but there certainly isn't as much maybe teeth in it, I would say. So the first sort of advanced concept or process around this part of the battery industry really came about, again, it was mid 2010s. GBS started working with Global Battery Alliance in Europe. It's primarily located in Germany, but a lot of reach in the EU. And the battery passport, anybody ever hear the term battery passport? It got a lot of press in early 2020s, but it's launching actually. Pilot was completed in 2024, and it's going to full launch in about 18 months or so. The battery passport is a digital tag that would follow a battery asset throughout its entire life. So the idea would be you could give the origin of the materials used in production of that pack, and then a digital signature would be used. Well, the requirements are they're using some kind of a QR code that would be tied to a traditional database. So, you've seen QR codes everywhere. You can scan them, and then it would give you the history of that, and it would include things like where the materials came from, that you're proving that they were not from a conflict supplier, and there would be a lot of use of tracking this throughout the different stages. So there would be a much clearer picture of where all these mass amounts of battery assets are. And this would be very, very helpful for making sure that we understand where the materials came from, but also very helpful if we want to start planning, for example, if we see, X amount of tonnage of a certain battery that's reaching the end of its usable life, we would understand how much recycling capacity we might need, for example. It just gives a lot of information to the industry. So in that way, it's designed, intended to help with creating circularity in the space, into making sure we understand what's out there, what's happening with it, and at any time we could find out, the history and even some performance characteristics. I know they want to try and tie some of that to it. Yeah.
So they're doing this in Europe, probably. Are we doing it here?
So I noted the SAE J3327. So there is a global battery traceability committee that I am a member of through the Society of Automotive Engineers. And some guidance was just published about traceability, but it's not the same extent as the battery passport guidance on tracing these assets. Exactly, baby steps. But yeah, everybody's looking at it and, it does make sense, right? So,
And one more question.
Yeah.
The battery passport or the identification is of a pack, not of a cell. Is that correct?
actually, it's on the cell,
Oh, it is on the cell.
which, okay, so that makes it very complicated
Oh,
if
yeah.
it's a scanning QR code and it's embedded in a sealed device. So I
Got it.
have a solution for you. So this was the same thing that we kind of scratched our head about, here we are, we're working on these packs. We understand this is a good idea. This is a good idea. But how do how do we make that actually reasonable? So one of the things that we sold with our company was a very large portfolio of patents around cell level traceability using ASICs, using a semiconductor that can actually provide, report out. It can report out through the control system or even on each cell, because using near field, you can activate that chip to give you information. It can have a certain amount of non-volatile data that it stores in it. So, this is sort of an interesting technology, and I know that ATC is still kind of working on how this will look in deploying this, and there have been some testing. We did some testing with Exalt Energy over in the old Dow chemical plant, over in Midland, and had tested some of this technology with NREL and DOE. So, there are a lot of really cool things happening in this cell level traceability space. And what this does is it allows, realistically, the United States to have a little bit of a leapfrog opportunity, because if you're using a technology that allows you to report out, that can be tied into some of the complex systems I told you about, like transportation. One project we did was putting this reporting sensor on a cell and then damaging that cell, but having it report out. So once the errant behavior started, it would report out externally to an onboard IoT device that can then say, we have an issue. These are the batteries that are involved in this. Reclamation would look like this. Here are the data safety sheets on that particular product. It can alert local first responders and say there's an imminent thermal event that's going to happen with these particular assets at this location. So lots of things can be tied in once you have a cell level traceability device on these assets. So I think this is the most exciting part of what's happening in this space. And it's also relying the most on research and development for deployment. So I'm hopeful that we'll continue to work in this space. But ultimately, cell level traceability tied with and fully integrated with the control systems becomes the most powerful way to help manage these complex and sometimes volatile assets. So there will be more, I'm sure, coming on cell level traceability. So that's kind of an overview of battery life cycle management. And yeah, love to take some questions.
You've been talking primarily about lithium ion batteries and presumably either NMC or LFP. The kind of the holy grail that the automotive industry is pursuing is solid state batteries. And there's, QuantumScape and Volkswagen are taking some real steps in that area. How much of the recovery and recycling capability that you're describing would be impacted if most of the industry went to solid state?
Yeah, that's a technology that I have not directly worked with. I've been able through the International Battery Association. I was on the board for many years and had a chance to talk with lots of companies that have gone in and out of the solid state space. And I've heard a lot, any minute now, these are launching. So that is not an area that I can speak to a whole lot. I will say that this technology in this space keeps changing. So I think that still traceability is going to be important no matter what. And some of the cell to pack designs, some of the solid state, we'll have to see. It's a question mark.
Well, just FYI, the QuantumScape company here in the US has a firm license agreement now with Volkswagen, and they are currently building a plant in, I think, the Netherlands that is going to be producing solid state batteries specifically for cars in the Volkswagen group. And presumably, QuantumScape has also been providing B1 samples to other manufacturers. Are you folks that are concerned with end of life getting any of these samples, or are you being included in the updates, if you will, on what's happening with that technology?
Well, since I retired in 2024, I haven't really been as involved in those conversations, but I do know that it's coming down the pipeline. We've heard that a lot. So there will be a lot of R&D and looking at those packs, certainly still thinking of the life cycle as it kind of laid out here, still applies. There will still be electronics, things that require repair. There will still be probably some full remanufacturing opportunities with those. My understanding is that they wouldn't have the same longevity because of their design. We wouldn't see the same cycle counts, for example, so longer lives. But I think that a lot of what we've just covered would still hold true. We'd want to use these and continue to use them in different applications to use them up before responsibly recycling them and then putting those materials back into our production.
So I guess I don't at all know what a solid state battery is. So does that mean it doesn't use any minerals? Is that what it means? I don't really know. I know batteries use minerals otherwise. I mean, the kind I'm most familiar with, like you were talking about.
I don't know the details, but you've talked about the various chemistries. It's much more like a solid state, like the chip industry and silicon and so forth. And so, but I don't know the details, but the idea is that because you aren't using the mix of the chemistry, it's more stable and so forth, but I don't know the detail. I haven't driven into that level of detail. I'm all about charging, so.
Okay, we'll pull together a session on solid state. That would be a good one.
My husband and I own two EVs. We drive electric exclusively. And we do get a lot of questions about the battery life. What are we going to do with it? And so I'm really happy to see the passport that they have established in Europe, and hopefully it continues over here, to keep track of everything that's going on and every attempt to recycle the chemistry and the minerals inside that, because I know rare earth is very valuable. You can hear about it in the news today. And it's really important that we recover all that and reuse as much as possible. So I was really happy to learn about that.
Good. Go ahead.
Couple of go ahead. Rick.
Safety of batteries, especially like batteries catching fire on airplanes, Chinese batteries that are supposedly not of high enough quality. Help me understand what's going on there.
Right. So that's really why I included, there are so many different levels of quality, which translates directly into the safety. And you hear a lot about safety of different types of chemistries, but they can all have sort of violent reactions if they're punctured or certain things exist in that space, the temperature, the way that they're handled, whatever. So I don't really think about safety as a characteristic, because they're all potentially very volatile. There are obviously issues with small electronics devices, large batteries that, will have some kind of self-discharge and cause some kind of catastrophic event. Batteries are everywhere. People wear jackets with heaters in them now, and pants and socks. And I mean, we have batteries in everything. And I think as a consumer as well, I do tend to look at devices and will spend more for a higher quality produced battery, where I know that the control system is going to be well tested, than ordering sort of an off-brand hoverboard, for example. We had the hoverboard issue, right? So, I think we have to be very cautious about that. And even a good battery and good control system can fail. And we've seen, some really horrible things happen with that. And we live now with batteries all over our homes. So yeah, I'd say just make sure you're buying quality stuff and look for anything that could be damage to it. If you drop something, make sure that you're getting these things checked out.
Another question on safety. There's been talk about this grid level battery that they're building up near Allendale. And I've been surprised at the negative press on that. Is that really something dangerous that people need to be worried about here?
We did some work for the Arizona Public Service Commission when they had several containers of batteries that went into full therm. And it is a violent, hot reaction. And those particular assets were in places where there weren't people nearby or other structures, but it's still a pretty scary thing when it does happen. So, I mean, I'm not familiar with all the ins and outs of what they're doing. I remember reading about that recently. I think that there's, just like with anything, it's good to understand what's being built and what's being used there. But personally, I think we need to have deployed energy storage on our grid for stability. So we have to, again, weigh the design and the build and the type of batteries that are being used for this, and who's building it, and the quality of the control systems that are in place, and the maintenance that's in place. And those are great questions to ask. But I wouldn't tend toward saying we don't want that, because I think we really do. But it's about doing it correctly.
So to answer your question, the grid level implementations are varying a great deal. There's different designs. I won't go into different designs, so forth, but some of them are NMC type batteries. But if you look at the implementations, the ones that I've seen, the cabinets are spread out in the installation. And they're generally not in the middle of a residential area and so forth. So I think there's a little bit of overreaction amongst the community. She's absolutely right that certain battery chemistries, you know, as most people know, once they start burning, you can't put water on them. You have to let them burn out. But there's also, and I talked to my grid class about some of the different chemistries that they're working on the grid. Because we're going to see batteries. We're going to see batteries in Holland BPW. And I talked about in the grid class that there's a high likelihood, this is a guess, but there's a high likelihood that when Campbell closes down, what's unique about Campbell in a power plant like that is the big backlog on the grid right now is getting a connection. Because all the simulation and the analysis they have to do of the electron flows of a given connection and what's produced and the demands and so forth. When Campbell turns into a field, the one thing that's going to remain there is the grid interconnection, the substation that's to the east of the property. I will bet money to anybody in the room that that will eventually become a battery installation. They would be foolish to give up that grid connection and not use it for that purpose. And as she's pointed out, we need a huge amount of battery implementations in the grid. And so, but there's time, you know, one of the I think it's Form Company, I can't remember the name, that's building a battery that how it stores energy is by rust. And so the rust and unrust, if you, I'm sure that's a word, but the rusting stores the energy, and then when you deplete it, it unrusts. And so they've built a 1 million square foot factory to build these kind of batteries, and they're being implemented in different parts of the grid. So there's just a lot going on there. But people get, the community reacts, but I would not be concerned. So that's probably more than one.
Well, if the rust thing really works, my 61 Bolero really.
Might add to the recycling opportunities, really. If they're looking for things that'll rust, we can all donate things that rust. You mentioned about catastrophic events when these things go, like warehousing them 15 feet apart. That probably isn't even enough, I'm guessing, 15 feet apart if they have a whole bunch of isn't, and what happens in that? I mean, I know they have tremendous fires. Do they release a lot of toxic chemicals in that process of burning? I mean, what are they gonna do if they, I'm not opposed to the Allendale thing at all, but what would it look like if the worst case thing happened there with their batteries? Because I don't really understand, other than I know if they're on fire, you can't put water on them.
Well, and actually, there are requirements if you're going to store a certain tonnage of batteries that you have sprinkling fire suppression systems built in. I mean, these are still important so that you're making damp any mass around these things so that so there are things that water is used for. And there are, I would say, again, if you think about how a battery is constructed and how much variability there is in the types of materials that are used, yes, there can be issues with air quality because of, you know, a plastic or acrylic that's in there or some other potting material. You know, there are lots of things aside from just the battery, the cell itself that are included in there. And it's a hot, very intense, generally very intense, fast burn when these things go off. And you can Google and see that. And I'm sure a lot of people do, but there will be, you know, there will be safety things built into these energy storage systems. There will be, you know, questions maybe to ask would be more about, you know, let's talk about the control systems that are in place. are the fire and first responders fully trained and understand? And there are a lot of great organizations out there that are doing that kind of work now, training firefighters, training other first responders on, how to address burns related to this, or, inhalation issues or whatever it is. So I just think they are being deployed everywhere, and we have them all over our homes too. So if we're really getting upset about one that's out in the field in Allendale, we might think in terms of, I have one parked in my garage all the time. So I think it's really about asking maybe the right questions about making sure that we can be safe should something happen. But again, that's very rare. Ultimately, depending on if we counted how many batteries are actually deployed and how many, they just look so shocking that people have a tendency to sort of cling on to that. But I mean, automobiles blow up all the time, internal combustion engine automobiles. So
Well, you
it's
mentioned
there.
this place in Arizona, and I assume that you said that it did burn, right? And I assume it just melted down and that was the end of it and they had to clean it
Yeah,
up, right? I mean,
it was containerized and they had,
Yeah.
some fire suppressant
Yeah.
in there. It didn't cause any damage externally, but
yeah.
Yeah.
They lost their product.
yeah.
This is a question from a novice. I don't have a hybrid and I don't have an EV. Who's responsible for those batteries that are in the field in all the cars now to go through that life cycle thing that you described? Who's responsible for those?
So there are a lot of different models out there being used by different automotive companies. There are some that are primarily a lease model, like the Teslas. That's a very important part of the Tesla model, is leasing those vehicles. And we've had some conversations in the special interest group here for HASP about, what is the residual value of those packs once the vehicle is no longer on the road. And it's really kind of gray because the company is really trying to control those assets throughout their life cycle. So they've got their own repair process at Tesla. They have very close joint venture relationships with recycling companies. A lot of the stuff is a direct to recycle model. So those are going directly to their recycler and they're trying to extract those materials. ATC Energy Solutions, ATC Drivetrain, the company that that my partners and I sold our company to here in Holland, is the primary battery life cycle management provider for General Motors. Most people don't know that. Every damaged General Motors battery comes to Holland. Well, that's a lot of batteries. That facility's big, but it's not big enough to have them 20 feet apart or even 10 feet apart. So, I mean, there are different ways that companies are approaching this. And the other thing to consider here is when you look at the use case of these assets, if you live in a city, you're less likely to have a garage, less likely to have charging of your own. There aren't thousands of chargers on the road for you to plug into. So if you live in an apartment building, it's very difficult to have an electric vehicle, full BEV vehicle.
If I understand what you said, is that the automotive manufacturing becomes responsible for the recycling or whatever use you're going to use with that battery.
There are different models. Some are very involved in that. Others are not at all. Nissan has a very robust sales arm for their used batteries. They sell them all the time. Leaf batteries are available. You can buy them online and people take those packs, maybe buy a new BMS. We've seen local companies. We've just heard about one that's fixing some themselves and redeploying them. There are a lot of companies out there that are doing it. It's sort of the Wild West when it comes to some of these home-built energy storage systems. That's a little frightening to me because these are very complex devices and there are a lot of people out there that are kind of playing around with them. Personally, and in my professional life, the only programs that I was involved in were directly with the automotive manufacturers themselves. but there are a lot of other things out there happening. And there are companies like Neo in China, they will swap a battery. You don't even charge it. You go in and it's designed to be swapped out with a fully charged battery. So you don't own that battery. No, you're using that energy in that battery for some period of time. So if you can think of a model, it's probably out there right now.
One way to think about who is responsible for these batteries ultimately, isn't it correct that because the rare minerals in the batteries are not depleted as the battery is used, they still have residual value, as you mentioned earlier, and that's an incentive for somebody to want those batteries to recover those minerals. Is that a fair statement?
Yeah, that's a really good, I think we're hitting the intermediate class of this, but I will give you an example. There's a lot of push right now for using LFP batteries, lithium iron phosphate, supposedly safer. I mean, safer relatively, right? Less likely to full therm and not quite a violent of a reaction, but okay, safer. Less expensive to produce. Don't use cobalt and some of these conflict materials. We saw some of the characteristics of that particular chemistry. And there's a big push they were going to build a plant in Marshall. I don't know where that stands. They were going to build a plant up in Goshen. There were lots of people getting into the LFP game. Cheaper, right? Better. The problem with LFP is that you don't have the materials in those batteries that we necessarily need again for new production. Yeah, they can be recycled and some of the materials can be reused, but it's not quite the same as like NMC or another cobalt chemistry where we want that cobalt. That's very, very precious. So what that means is there isn't, there's not an imperative, there's not an incentive to go direct to recycle with LFP. But we certainly don't want to go to landfill. So we have even more of a incentive to find a way to use these in some second life application because there just isn't going to be the value in recycling those. We know we'd have to do it environmentally, but the materials are not quite as valuable. So depending on the chemistry that's in use or kind of what's the popular choice or what companies are trying to get into, that can have a really big impact on all the flows that we saw.
You asked a question about recycling. So in the Tesla world, a huge amount of their battery packs come out of Reno, Nevada. And like, I don't know if it's across the street or right close by, is a huge Tesla. Well, it's not owned by Tesla. It's a different company.
Redwood.
What's that?
Redwood.
Redwood, who does recycling of Tesla batteries. And so, for example, in a Tesla that you buy today, the battery pack, it's been quoted as much as 30% of the critical materials in what you buy today came from an old Tesla battery pack that was recycled. So they've taken a very aggressive approach to the recycling issue. I don't know all the details, but that's one piece of information that I do know about.
You mentioned that the economic incentives for recycling LFP batteries is not as great with NMC. Both Ford and GM have recently made announcements about moving to a lithium magnesium rich LMR battery. Do you know whether the economic incentives would be better or worse there than with LFP?
I don't on that particular chemistry. I do not.
I guess I'm next here. Before we bought our EV, I was concerned about batteries too, fires, and you hear all this stuff in the news, and it took me a while to get comfortable with it. And I've come to the conclusion that energy is never without consequence. Whether it's a gas engine where you have 26 explosions going on constantly in a normal gas car, or you have an EV. And so after a lot of research, I became comfortable with the EV and we love it. But it is a technology people aren't familiar with. And there's a lot of press out there that talks about a bad situation, but they don't talk about all the million other great situations that you have. And that's true for all new technology that comes in.
There's a lot more fires in ICE engines than there are in battery cars, by the way, just throwing that out. They might not be as bad, but they do exist. The other thing is if you own one of these EVs, and talking about my wife getting accustomed to it, the battery, the BES or battery management system is always working to make sure the battery pack is in the optimal temperature. And so there's times when you get out of the car in the summertime and there's a fan somewhere cooling the battery pack and you're walking away. And my wife initially used to say, the car's not off. And so you can go out in the garage and all of a sudden the fan's running or it was running. And so it's constantly working to keep the environment right for the battery.
That's its job. So before we wrap up, I did want to say I still am very connected with the ATC organization here. I'm still a shareholder of the business, and I see the general manager quite frequently. They have offered to allow us, this isn't sanctioned through HAS, but if anybody's interested in maybe doing a tour at ATC and being able to see some of this in life, real life, so that reverse supply chain. So I've got my email address up there. Just shoot me an email, and I'm thinking about trying to schedule something maybe in November
Great.
or early December, and we can just, head over. It's on Waverly. It's in town.
I'll follow up with you on that.
Okay, perfect.
Great. One last question I'd like to ask is the passport concept in Britain sounds like a good one, but it sounds like what you were describing, that each individual cell would be able to report its condition and what it is and what its condition is. Ultimately is the ultimate solution to controlling every single cell and every single huge battery. Is that correct?
Yeah, so maybe another intermediate topic, but what could be really interesting about cell level control system. So what we're talking about here is transitioning from this BMS that sits on top of the battery pack and responds to thermistors saying it's too hot and does something, or, it sends out, tries to, smooth out charging and discharging, but it's very aggregated on the whole battery. When you have a device that can actually perform a lot of those things directly on the cell, you have some interesting protective and control measures that you could never have over the full pack. For example, it would allow you to, theoretically, if you added some kind of a shunt, you could electronically render a cell inert. So what does that mean? That's very interesting to the DoD if they have stranded battery assets and somebody can't use them because they've been electronically rendered inert. That's very powerful. Similarly, if there's some kind of a potential thermal event that could happen, that cell could be circumvented from charging to avoid it shorting out the system. You'd see a depreciation in your capacity, but ultimately you'd be able to avoid one cell or a group of cells and continue operating that vehicle for some period of time. So theoretically, there's a lot that can be done when you have cell level control. The other benefit of cell level is being able to, from the moment that cell is in formation, right? We were talking about when is it a battery? A cell that goes through production spends a significant amount of time in testing before that asset can be used or integrated in any way. So it's, sometimes days that they have to test to ensure that they understand the capacity. So they're charging and discharging a brand new cell at LG, for example. Well, that leads to a ton of scrap of materials. But if you could do that testing on the cell without having to move those around or even get better reporting directly from that cell, you're digitizing that manufacturing process. There are a lot of benefits to how grading and sorting could be done more efficiently in manufacturing. And then, of course, grading and sorting throughout every other step in the life cycle. But
Any other questions? Comments? Kris, I'd like to thank you very much for
Yep.
a complicated situation.